During my recent video on DDT and the California condor, I said, during these reactions, chlorobenzene is ortho-para-directing. That means substitution will occur either next to the chlorine atom or opposite the chlorine atom, with the para position, the one opposite the chlorine, being favored, but gave no justification for it. It was simply a trust me moment. Well, today we're going to discuss electrophilic aromatic substitution and how different substituents can affect the position at which these reactions occur. Good afternoon and welcome to hand-wavy chemistry. Electrophilic aromatic substitution reactions occur when an aromatic compound, like benzene, reacts to replace one of its hydrogen atoms with an electrophile. To understand what makes these reactions so interesting, let us first consider what happens when we react a non-aromatic compound that contains a carbon-carbon double bond. For example, the reaction of cyclohexene with chlorine. When cyclohexene is exposed to chlorine, we get addition of the chlorine atoms across the double bond, giving 1,2-dichlorocyclohexane as the final product. However, when benzene is exposed to chlorine gas, we do not observe any addition reaction. Instead, we see the very slow substitution of one of the hydrogens for a chlorine atom. Now we can speed up this reaction by adding a Lewis acid, such as aluminium trichloride. But we will still only observe substitution. So what's going on? Let us consider the catalyzed reaction. Chlorine binds to aluminium trichloride, effectively giving us a source of Cl+, an electrophile. There's all these electrons in our aromatic ring. So, our carbon-carbon double bond can break, it can reach out and grab that Cl+. In doing so, we generate a carbocation. But this pi system is conjugated, so that carbocation can be moved around the ring through resonance structures, which stabilizes the intermediate. Eventually, the ring is going to want to go back to being aromatic, so it needs to either kick out the chlorine or the hydrogen. If the chlorine leaves, well, we're just back where we started. But now, if that hydrogen leaves, we have a different molecule. We now have chlorobenzene, and we have performed electrophilic aromatic substitution. Now the question becomes, why do different substituents affect the position at which these reactions occur? And there are three main things we need to consider. The first is that these aromatic systems are reacting with an electrophile, something that loves electrons. So if we can increase or decrease the electron density at different positions within that ring, we can change the rate at which those positions will react with an electrophile. Secondly, if we can stabilize that carbocation intermediate, then we lower the activation energy and the reaction will occur faster. And finally, there are steric effects. Large, bulky groups that just physically block certain positions from attack. Let's start by considering aniline, a benzene ring with an NH2 attached to it. Now that nitrogen has a lone pair, which it could bring down into the ring, generating a carbanion in the ortho position. But remember, this is a conjugated system, so we can draw resonance structures that spread that negative charge between the ortho and para positions. Aniline is electron donating and ortho-para directing. Now consider nitrobenzene. Our NH2 is now an NO2. There is no longer a lone pair available to bring down into the ring, but rather we could take electrons out of the ring, generating a positive charge in those ortho and para positions. The nitro group is electron withdrawing and meta-directing. In both of these examples, we could draw resonance structures, putting charges into the ring and predict from that how they might react. But what about if we had a substituent that we couldn't do this for? For example, a CH3 group. Well, in that case, we need to look at the carbocation intermediates and determine which configuration is the most stable. For toluene, reaction at the ortho or para position generates a set of resonance structures that includes one tertiary carbocation and two secondary. However, reactions at the meta position only generate secondary carbocations. Because tertiary carbocations are more stable than secondary, the CH3 group in toluene is ortho-para-directing. Now, what if we had CF3 instead of CH3? You might initially think it would be exactly the same, but those fluorine atoms are strongly electron withdrawing. They're putting a partial positive charge on that carbon. So if we were to put our carbocation adjacent to it, we're bringing two positive charges together, which is disfavored. So actually, an electron withdrawing substituent like CF3 is meta-directing. And in general, all electron donating groups are ortho-para-directing, and all electron withdrawing groups are meta-directing, with the exception of the halogens. The chlorine in chlorobenzene is electron withdrawing, but it is also ortho-para-directing. So what's going on there? Let's look at the resonance structure where we have the positive charge next to the chlorine atom. The chlorine, although electron withdrawing, does have a lone pair, which it could bring down to generate a double bond. As a result of doing this, our carbon now has 4 bonds on it and no longer violates the octet rule. Now, halogens aren't great pi donors, but we can look at our experimental results and rationalize that they must be good enough. Finally, the reason why chlorobenzene prefers para substitution to ortho substitution simply comes down to sterics. Chlorine is much bigger than hydrogen, and so it more effectively blocks the sites around it. Something we haven't really discussed is the types of electrophiles that can be used in these reactions and the conditions under which the reaction proceeds. But that is a story for another day. I hope you have enjoyed this video, and if you have, please make sure to like, subscribe, and share it with your friends. And if there is a topic you'd like to see covered in a future video, please put it down in the comment section below. Thank you, and I hope you have a wonderful rest of your day.